Thank you, Julie. We're delighted to welcome back Dan Purich. I don't know if this is the third or fourth year in a row that he has talked about the Nobel Prize in Chemistry, but we keep inviting him back because he's one of the few people who can talk on this topic that the audience has a chance of understanding what it's all about. So we very much appreciate that. Dan is notable because I think he gives more hours of lecture in the College of Medicine than possibly any other member of the faculty. And they got a new chairman in his department of biochemistry, and the new chairman noted that Dan was supposed to, said he was going to retire, I don't know when, next spring or something. And the guy said, no, I can't afford to have you do that because I have to be able to recruit new young people, and we can't load them up with all the lectures that you otherwise give for us. So there's a good relationship at this moment with the new chair. And that's good because Dan himself was previously the chair of the department for a fair number of years, probably about a dozen or so. And he came here around, so I remember, probably 1983 or something in that
overlapping
range.
with your leaving.
Yeah, just as I was leaving to go to New York, then to Cornell. And so prior to coming here, he was a professor of chemistry, I think, at the University of California, Santa Barbara, which was the only faculty position I think he had had prior to Florida. He had managed to do a year of postdoc work at the NIH with Earl Statman in his laboratory, and that was after he finished his PhD at Iowa State University. So we have this slide that he very nicely made for us, listing his career. You all can read that slide. I don't have to repeat it. But I think I'm looking forward very much to hearing Dan today. So welcome, Dan.
Thank you very much. Thank you. It's great to always come back and see Ken and have the opportunity to present a little bit about the Nobel for the previous year. As I do this year in, year out, I noticed that I'm getting to an age where I share the age with old people. This is a new fear of mine because at 77, I don't know. I guess I could say that when I was a graduate student, I stayed at my advisor's home too long one night, and a noted Academy member, Henry Lardy, turned to my advisor wanting to get to sleep, and he said, Herb, what's your definition of a good graduate student? And Herb had no answer, to which Henry said, someone who doesn't know the party's over. Okay, and so as far as teaching, I haven't yet decided that the party is over. And I enjoy this opportunity to tell you more about the Nobel for the past year. So I can control the slides from here, Julie.
Yes, sir.
And this award was given to 3 investigators, and Carolyn Bertozzi, Morton Meldal, and Barry Sharpless. And it was for, as it says here, the development of click chemistry and bio-orthogonal chemistry. Click chemistry has become a very important area of biochemistry and medicine in recent years. So let's take 1 minute and get familiar with a little bit about each of these individuals. Bertozzi is a professor at Stanford, 56 years old at the time of the prize, Harvard BA, and then went to Berkeley for her master's and PhD. Then she moved across the bay to UC San Francisco, where she worked with Stephen Rosen. And if you were to look up her hobbies, she says the favorite thing she does is tweet bright students. She noticed the students in her class, and she sends them little tidbits that she thinks would stimulate their mind. Morten Meldal is at the University of Copenhagen, where he was born. He got his BS and PhD in engineering, chemical engineering and chemistry, and then did a postdoc at Cambridge. And his hobby is oil painting. And the last of the three Nobelists, and here you see two medals up here on the right, because this gentleman is twice a Nobel Prize winner, and that's a rare distinction. As you know, Madame Curie got 2 Nobel Prizes, and my hero, Linus Pauling, got 2, but not in science. One was on a more important topic, nuclear non-proliferation. But Barry Sharpless is at Scripps, born in Philadelphia, Dartmouth undergrad, Stanford PhD, and then he worked for another Nobelist, Conrad Bloch, at Harvard University. Conrad Bloch had a lot to do with the synthesis of cholesterol and many other important molecules. And appropriately positioned at Scripps, his hobby is deep sea fishing. So gives you a little bit of an idea of who they are. And what I want to do is just, for people who don't know much about organic chemistry, I want to introduce a few things that can help organize your thoughts. So we'll start with the very beginning of organic chemistry. And this started when Wohler was able to heat ammonium cyanate, and he made this molecule, which is urea. And this is actually the original paper, which I could have gotten from Ken Burns, because Ken Burns, you may not know, is the younger brother of the 3,000-year-old man. Ken Burns was probably around when Wohler did this work. 1828, were you around back then? You might feel that you were. I see. Right. So after Wohler, it turned out people were very successful. And when I took organic chemistry in the early 1960s, textbooks were very proud to boast that in that period of time, over 200,000 novel molecules had been synthesized. And it further said that about 5,000 molecules were being synthesized per year at that time in 1960. This attests to the inventiveness of organic chemists. But now, in 2020, this number is 180 million. So quite a big difference between that number. And it speaks to the industry and the inventiveness of organic chemists. And it also hints at the vastness of organic chemistry, that there are all these compounds out there that you could make, some that you might not care to make, but others that could be very useful. And so when we think of organic chemistry, it all starts with this molecule methane, which has 4 hydrogens around it. And if you were to put a plane from this hydrogen, this one, and do that successively, you would notice that it would make a triangle, a pyramid made of triangles. And that's why we call this molecule a tetrahedral molecule, or tetrahedral carbon atom, because it is at the center of that little pyramid, tetrahedral pyramid. And this molecule is just the beginning, because carbon can form single, double, and triple bonds. And as it does so, this is ethane, this is ethene, and this is ethine. And these bonds are formed because carbon each carbon atom has electrons and has orbitals that allow for these electrons to overlap with neighboring carbon atoms if you figure out a way to coax them to do so. And they will make carbon-carbon single bonds, carbon double bonds, and carbon triple bonds. The single bond can rotate freely. Double bonds are constrained by that double structure, so they cannot rotate. And triple bonds tend out to be very linear. And they're interesting, triple bonds are, because they have so many electrons. Each bond is actually made of one electron from one carbon atom, one from the other, and they're overlapping and they're forming bonding orbitals. And so this molecule that has a triple bond has a lot of electron density located right in that region. And this will be part of the story of click chemistry. Now, the other thing that happens is that bonding can lead to further complexity because we can make chains. We can make chains such as the 3-carbon molecule here, propane, natural gas is largely propane and methane. And so here, this molecule is held together by carbon-to-carbon bonds, forming chains. And the same kind of bonding can also lead to ring-like structures. And we can form, for example, in the case of benzene, we can form these hexagonal rings that are very flat, and we can build up structure by adding side chains off of each of these carbons. And in doing that, we end up being able to make a myriad of different molecules. And again, it's the inventiveness of organic chemists how to do this. And at the center here, I show you we can make new molecules and then we can test them. And if we learn something about whether they bind to a certain drug receptor or not, then we can help to design new molecules. We can test them, and we can keep doing this until through multiple iterations, we design molecules that fit very well in enzyme and receptor sites and become the basis for new drugs. And so the enterprise of organic chemistry isn't just for what molecules we can make, it's for making useful molecules, very valuable molecules. And it's not just for medicine. It turns out that a friend of mine, Fred Woodle at UC Santa Barbara, has worked for a number of years on plastics that can be self-healing. That is to say that when the plastic polymerizes to make the polymeric structure, it leaves within its structure some of the unreacted monomers, unreacted groups. And as you break the plastic, we drop phones, we drop all sorts of things and break them, that then all you do is put the plastic back, push on it a little bit, wait a couple days, and it's good as new again, because they're self-healing plastics that are being developed through organic chemistry. So there are a lot of very useful things, because nothing is more useless than plastic after something is broken from it. It ends up floating in the ocean. It ends up in many places we don't want it. So it's much better if we can heal those molecules, bring them back to utility, and then take advantage of that. Another feature of this carbon having 4 bonds around it is that if we make each substituent a different substituent, then these molecules can have handedness. That is to say that this amino acid shown over here and this amino acid shown over here are mirror images of each other. It's as though we have a mirror sitting right in the center here, and the little pinky is close, the thumb is far away from the mirror. And likewise, this hydrogen is far away here as this one here from that mirror plane that's in the middle. And if we're under normal conditions, when we make these kinds of molecules, we would end up on average with 50% of them being what we call right-handed and 50% being left-handed. And this handedness is important in biology because enzymes are made of asymmetric units, L amino acids, and they engage their binding partners in showing what we call stereoselectivity. Enzymes prefer to bind one of these versus the other, and nowhere is that illustrated better than in this next structure. Here I show you the structure of a molecule called palotoxin. And palotoxin, every place where you see a large, bold bond, shown as a long triangle, or where you see these dashed lines, wherever those are seen, the carbon atom that's holding them is asymmetric. That means it's either of the right-handed or the left-handed form. So there are, in this molecule, 71 different sites that are asymmetric. And since each one could either be right or wrong, right or left, then you would end up 2 to the 71 possible forms, which is around 10 to the 27th. It's a very big number. Again, reminding us of the vastness of organic molecule space. And we call these forms stereoisomers. And even though we could potentially make 2 to the 71th of those, a very large number, it turns out that palotoxin is only made of one unique form of these, and the organism that makes palotoxin only makes this one. And the reason why it only makes that one is that these molecules are being made by enzymes, and enzymes have absolute stereospecificity, so they're only making the product that they want. This is how nature doesn't have to make a ton of different molecules, it just makes the one that really matters. Since we're talking about palotoxin, I thought I would diverge for a minute and tell you a little bit about it. It's a toxin that coral produce. Coral have a disadvantage in the marine environment. They're stuck to this large structure, a coral reef, and as fish float by or swim by, what they do is they produce palotoxin, and the fish consume this by it's in the water right next to the coral. The corals actually eject it so that when a fish comes by, they sort of spray the area with this. And in 1 to 2 seconds, they paralyze the fish, and the fish just drops onto the reef, rots, and the coral then have food. So it's a very clever way. And the way they're able to do this is this molecule is binding to the pump that's in every cell of our body. We have pumps, miniature protein molecules, that pump sodium ions out of cells and potassium ions into cells. And that's what gives us the electric gradients for nerve conduction and for the cells to survive. So once this molecule binds to that protein, it opens the pore of the protein and allows sodium ions to come in when they shouldn't, and potassium ions to leave when they shouldn't. And now the electrical potential of every neuron in that fish is 0. And you know, once the system comes to equilibrium, that's the characteristic of death. And so the fish dies promptly or is paralyzed promptly. Now, palotoxin is also an interesting molecule because my favorite mass murderer, Agatha Christie, who is always killing off people in different ways, she used all these different molecules here in the 28 murders that she committed in the Poirot series, and even more when you think about the Marple series. But all of these actually are pretty crude inhibitors. Arsenic, it takes grams of arsenic to kill someone. It takes even 100 milligrams of cyanide to kill someone. So these are pretty clumsy when you think that palotoxin in humans, it'll kill a human in 1 hour with 5 micrograms. And for comparison, a nickel weighs 5 grams, so 1/1,000,000th the weight of a nickel is enough to kill a human being. So I love Poirot so much. I've watched that series in BBC so many times that I had to mention Agatha. Now, here is an example of the power of organic chemistry. there's a molecule called Taxol, more important to women than to men because it's used to treat ovarian cancer and is highly successful in doing it. It's a molecule that is almost impossible to synthesize from basic elements because it has such complexity to it. This is a large ring structure that's very unmanageable in the synthetic laboratory. This molecule is obtained from the bark of a Western yew, Taxus brevifolia. When it was purified and studied, actually I did some of the early studies, and a friend of mine, Susan Horwitz at Einstein, figured out first that this molecule binds to the fibers that allow for cell division. So every time you see chromosomes in cells dividing when you look in a textbook, those fibers are called microtubules that are holding them and guiding them to the right destination. And this molecule, when it binds to it, screws up those structures so that now dividing cells can't divide. And cancer cells, as you know, divide more frequently than normal cells. My wife's a pathologist. When she looks through the microscope, she counts up how many dividing cells there are and how many per 100 of cells. This gives her what's called the mitotic index. And so cancer cells are dividing 4 and 5 times faster than normal cells. And so if you can stop them with a drug like Taxol, yes, you'll kill some normal cells, but you'll kill the cancer cells. And that's the strategy. But this molecule is obtained from the Western yew, which is on the northwest coast of the United States. Other forms of this, other genuses don't have, other members of this genus don't produce Taxol. Now, the reason why the plant is producing Taxol is the same reason why tobacco plants produce tobacco, not for us to smoke and have the nicotine, but nicotine is a poison. In fact, in that list of Agatha's poisons, nicotine was there. It was used in at least 2 of her episodes. But here, the plant is making Taxol, so if any predators come along and want to chew on the bark, they will be killed by the Taxol. And we call these secondary metabolites. These are molecules that aren't necessary for life, but give us some benefit. So these molecules are, in this case, very complex. And if you think about it, they're in high demand because there are enough women worldwide that have ovarian cancer, and there's not enough of this plant. There's not enough of it to meet the demand for Taxol. And so about 25 years ago, it was recognized that if you were to use every plant on the West Coast, that you would have enough for about 1.5 years worth of Taxol. And then you would not have any anymore. And so the answer to this problem comes in the form of semi-synthesis, again telling us why synthetic organic chemistry is important. Because the leaves of Taxus brevifolia, these leaves contain lots and lots of this molecule. And this molecule, if you look atom by atom, has a lot of similarity to the final product, Taxol. So investigators at Florida State University found a pathway for converting this molecule into Taxol. And since there is so much in the leaves, and the leaves would accumulate, and by the way, these leaves, when they fall to the ground, people had always wondered why no animals ate these leaves. They're so poisonous. It's because this molecule has a lot of the properties of this one, not as much as we would like, so we have to make this molecule. But what this means is that synthetic organic chemists, through their talents, were able to figure out ways to make the molecule and maintain an adequate amount for the needs of women that are confronting that cancer. Now today, when we do this organic chemistry, we're largely depending on graduate students and postdocs and undergrads to carry out the manipulations. But now, in the last few years, investigators at many universities have gone over to robotic synthesis, where you, in this little position right here, you put a stack of maybe 20 stacks on top of each other, a bunch of little test tubes that become reaction centers. You have all the different reagents you want, and you carry out various synthetic reactions robotically. And the advantage for doing this kind of robotic synthesis is that you now can look at all the permutations of temperature, of concentration, of acidity, all the different things that you must optimize in order to get a reaction to go. So organic chemistry, as good as it is, requires a lot of futzing. You have to futz around with this condition, futz around with that condition. And graduate students get tired of that, but robots don't get tired. I have a robot that has learned the shape of my swimming pool. I just put it into my swimming pool. I press a button and it cleans my swimming pool. And I love it. And I tell my wife that I cleaned the swimming pool, for which I get absolutely no credit because all she does is lifts her finger up and down to remind me that all I did was flip the switch. But robotics reminds us that there's all this futzing around in chemistry. So what happens is that to make chemistry more reliable, certain people have identified certain reactions that are particularly versatile, particularly helpful and particularly predictable in their properties. And they become so predictable that people are so pleased by that they name the reaction after the person. So we call these named reactions. And for example, there are about 25 methods for making carbon-carbon bonds and carbon-carbon double bonds. And almost every one of those methods has been rewarded with a Nobel Prize. It's quite amazing. If you can figure out a way to make a carbon-carbon bond in high yield, like the Grignard reaction or various other reactions, you can get a Nobel Prize. One of the master's degree graduates at UF Chemistry, a guy named Robert Grubbs, succeeded in doing this and created something called Grubbs catalysts, and that got him a Nobel Prize. So there's a reward in getting reactions named after you. It's because the reactions are so useful, but they're highly recognized. Their utility is valued. In 1960, when Ken and I Ken had already finished organic chemistry, I was just getting ready to take it, there were about 50 to 60 named reactions that we had to learn. And we were always at pains to learn these because, particularly in his case, because he had studied organic chemistry with Louis Fieser, who was the consummate synthetic chemist of that time. And over 300 reactions are named reactions, and whenever you see them in textbooks and journals, they don't tell you the name of the chemicals, they tell you the name of the individual. And Barry Sharpless, who I mentioned earlier, invented 4 of those reactions. So if you look at the list of all these different reactions, if you look very carefully way down here, you'll see this name Sharpless. And just for those of you in the back, I've amplified that region. You see there are 3 of the reactions named for Sharpless: amino hydroxylation, dihydroxylation, and epoxidation. Whatever those words mean to you, those words to a chemist mean opportunity to make molecules in ways that they couldn't before. And if you go further on this list, you find this one marked click chemistry. And that's the one that we will talk about because that's the one that got the Nobel Prize. So what Sharpless realized was that there's this whole lot of opportunity to make molecules, but you have to futz around to get them to do what you want to do. And so you might have an idea for making a molecule. You know the reaction because other people have done that reaction with a different chemical structure. But now to get it to work for yours might take 6 months or a year. So what he wanted to do was find molecules that would be much simpler, the reactions would be simple to perform, because many reactions, if they're in Ken Burns' hands, they'll never work. If they are in my hands, they might work 1% at a time. And if they were in the hands of one of our organic colleagues, they'd work all the time. Yeah? It's a safe assumption, I think a very safe one. So click chemistry is a term that was introduced by Sharpless actually in 1998, but by 2001, he said that they should be simple to perform reactions that have high yields, so you're not wasting a lot of material to make what you want, that they're broadly useful, because why make something if you can't use it, that they created easy to remove byproducts, because if the byproducts you had were toxic, you would have a problem, so you want to be able to remove them. That were stereospecific. Remember, we talked about right-handed and left-handed molecules, so you want to make them so that they will do that. And that can be conducted under conditions where we're using low toxicity solvents. For example, many times in a chemistry lab, you use benzene and toluene. And these molecules are not completely innocuous. They can actually, some of them cause cancer. So his goal was to identify simple and reliable reactions that can occur quickly and that could avoid these unwanted products. By the way, I thought that they should have been able to put a smile on the guy's face. He always seems to be grimacing a little in this picture. So what he wanted to do was make reactions that would pretty much snap together. And recalling he says in one of his commentaries that he was at his daughter's house and watched his granddaughter assembling Legos, and they click as they snap together. And he said he wanted these reactions to click together, and that's how the name click chemistry came about. And the other thing that he wanted was he wanted it so that chemically unskilled researchers could use these reactions. And this, you might wonder, why would you want chemically unskilled researchers to do this? Well, you might have someone that's working on DNA in a chromosome and wants to introduce a fluorescent molecule on part of the chromosome. And this won't typically be done in an organic laboratory. It's going to be done in a biochemistry or pathology department. So he wanted one to be able to do that, just like you click together certain of these components. And he wanted it so that from these simple building blocks, he could make any desired product that he has. This sort of looks like a llama to me, but you can do with it in your mind what you will. But I thought that it was kind of fun to sort of show a product. So we can create an endless variety of molecules. We've seen what can be done with Legos. Biochemistry and organic chemistry is way beyond Legos. And not long after he came up with this goal, he and Medal, working independently of each other, quite remarkably, developed the very same reaction. And that was because about 3 years before, another named reaction had come into use called the Staudinger reaction. And they were both thinking about this reaction. And that got them to develop what's considered the perfect example of click chemistry. And now, you will forgive me, but I'm going to actually show you technically what this reaction is. It may be painful for you for a minute, but bear with me, and you'll see what's happening. So here's that carbon-carbon triple bond molecule. Whenever we draw, we take the carbon atoms out of the drawing, and wherever there's a methyl group or some group over here attached on its end, that's the triple bond between two carbon atoms, and then that hydrogen's attached to that carbon. And if we take that alkyne and we bind it to copper, copper has some vacant orbitals in its atomic structure so that it can allow for it to make a complex. And when it does that, it makes this molecule more reactive. And then a second copper atom comes in. And when they do this, now they've made this so that it's all set up so another molecule called an azide can come in. And when they do that, now all the different partners, everybody's been invited to the party in the right order and in the right geometry. And now electrons can move, and pairs of electrons move from this carbon to that nitrogen, from this triple bond, they move over to here. And as they do that, they form a new molecule, which then, as the carbon leaves, they form this product, which is then released. So by going around this circle, we get back to this point, and the copper can be used again. And this defines the copper as a catalyst, because a catalyst is something that makes the reaction go, but is not consumed in the reaction, and typically makes the reaction go faster. And the copper makes this reaction go about 800 times faster. And this is called copper catalyzed azide alkyne cycloaddition. A lot of words there. But you get the idea that they can control the chemistry and they can make molecules. And when you take this chemistry and you set it up in a little kit that people can take and use, they can use this chemistry in a very versatile way. For example, with click chemistry, Ken knows I can't get very far away from DNA in one of these lectures because he loves DNA, and I have to, feed our friendship. So here's a chromosome with DNA, and here's a molecule that can be converted to eventually to deoxyuridine, then to deoxythymidine, and it can get incorporated into the DNA of the chromosome. So sitting out from this chromosome here, you see all these triple bonds sitting out there, and now that's equivalent to here, the DNA double helix with these molecules partly there. So now what's happening is with that chemistry, the click chemistry, we can take copper plus that triple bond, plus we put the azeto group on a fluorescent molecule, and we can now fluorescently label the DNA. And we can do that to compare what's happening in a healthy cell to a diseased cell. We can use different dyes, then we can overlap these. We can find, by differential chromosome labeling, we can learn certain aspects of pathology. There are hundreds of examples of click chemistry, and I'm not going to go through all of them today. But when Bertozzi came along, Carolyn Bertozzi recognized that copper catalyst was too toxic for living systems. So if you're working with chromosomes that you've isolated, you can label with it. But if you're trying to do some reaction in a cell or in the body, the copper is pretty toxic. So she decided she would figure out a different way to do this. So what she did was she developed a workaround that eliminated any need for copper in the reaction. And she did this in a very clever way. What she did was took this reactive alkyne and she put it into a complex ring structure. And then this ring structure was strained. It had a conformation that it didn't like to be in. And then as the reaction of the alkyne with the azide proceeds, then this ring would change its shape, and that would drive the reaction forward. And she called this method bio-orthogonal chemistry to indicate that the reactions could occur without harming a living organism. So this word orthogonal means without effect on something else. You know, when you take a tuning fork and you hit the tuning fork and it's vibrating, if you bring another tuning fork next to it, the energy from one will transfer to the other. But if I turn them at a right angle to each other, no energy will transfer. And so when we can arrange structures that are orthogonal, we, in this case with the tuning forks, no energy, what she was doing was setting out chemical reactions that wouldn't interact with living systems in a way that would harm them. So she called that bio-orthogonal chemistry. And an example of that is shown here. She could deal with a tumor here, and if we were to look at one tumor cell and blow it up really large, this is the membrane of one tumor cell. And she would use antibodies, a multi-antibody to a receptor, so that's this region here. It's made up of multiple units that will bind very firmly, not a single typical antibody. And when it binds, then it would bring the rest of this molecule to the party. The long sinusoidal-like molecule there is polyethylene glycol, which has a lot of side chains. So when this molecule binds, and that polyethylene glycol is sitting out there, and it's very long, it even goes off the slide here, then there are many of these attached to it. She's only showing you one. And once it's in position here, she could add a molecule such as this, and it would react with the azide under normal conditions. You see the ring is strained here. It's not a nice open ring, but it's driven to its more open form. That energy that was stored up in the strain of this molecule is actually helping to push this reaction along. And as it does so, she can cleave off the rest of this molecule and cleave it off locally right at the tumor cell. And this molecule can enter the tumor cell, and being a very potent inhibitor that would otherwise kill every cell in the body, now she's able to deliver it locally and kill only the tumor cell because the drug has been delivered there by the specificity of the antibody. And so this method is a very clever way to deliver a drug to where you want it and to prevent the drug from just causing other effects. Because the big problem with drugs is they have off-target effects. So you may be able to inhibit the cancer cells, but then you cause all sorts of other problems. So she has developed a way for targeted drug release. Now, this shows you the path that was taken to this Nobel. In 1998, Sharpless had the big idea of he wanted to make these certain molecules. And he just put it out as a dare on the literature, saying, who can make one of these will do something great for science. But he also had some ideas that he could do it. And so he did it, and Nobel did it, and they carried out a reaction that used copper. Meanwhile, about 1.5 years, 2 years later, Bertozzi came along, and then they started to use these in many different inventive ways on DNA, on proteins. They could label cancer cells. And now there are about 20 drugs in the pipeline that are based on this molecule. And these elegant and efficient reactions have become very popular. Click chemistry, in the 20 years since it was first recognized, has 220,000 literature citations. That's anyone who knows about literature citations, that's a pretty remarkable number. And if you go to the literature, go to Google Scholar and put in click chemistry, you'll get this paper by Sharpless from Angevantica Chemie International Edition. And there are 16,000 citations to that paper alone. It's really quite amazing. And because Ken is who he is and his love for DNA is what it is, I want to compare it to the Watson and Crick paper, okay? Because we all know the Watson and Crick paper. The Watson and Crick paper will be 70 years old on the 27th of April of this year. And since that time, it has been cited 17,373 times, only a bit more than that other paper in 20 years. But in all fairness, I would never try for a minute to tell you that their discovery matches the Watson and Crick discovery, because people just said Watson and Crick. They didn't even bother citing the paper. And so when I put in the words Watson and Crick and look up all the citations that are there, it's 27 million papers. Okay, so I do want you to know that it's quite a lot of citations. But it's telling you that in those 20 years, remember, when we talk about DNA, we're talking about something that's affecting biologists and medical doctors and so forth. When we're talking about the stodgy area of chemistry, to get 16,000 references is quite remarkable. So bio-orthogonal chemistry has gotten about 30,000 literature citations in that time. And all of this is the basis for them getting the prize last December 10th. And with that, I'm happy to answer any questions.
Me too. Questions?
A masterful lecture.
Oh, thank you very much.
So beautiful.
This was all Saturday, as I said.
Yeah.
I got very unpopular at home, but I feel that if I'm going to lecture here, especially sometimes to people who haven't had an organic chemistry class, I want to make it so that it's absorbable.
Well, I had organic chemistry and I barely got through it. So but the elegance of this, of science in general,
Yeah.
is exemplified by this work.
Yeah.
So I want to talk about catalysts in general.
Yeah.
They're oftentimes in the laboratory, a catalyst allows you to do something without heating it up, because heating up is another way of supplying that kind of very or rapid movement of molecules, and they're likely to react somewhere.
Right.
And obviously heating up is not healthy for living things.
Right.
So when we have the bio-orthogonal discovery, what you're doing in effect is through the energy that is being
Stored up in
that unpleasant molecule,
Right.
offers that kind of energy to utilize.
Yeah,
in
it's
getting the reaction
localized,
going.
and so on a per molecule basis, the energy is right where it's needed to drive the conformational change that drives the chemical reaction.
Tremendous. Yeah.
Whereas, and it's not a catalytic reaction. The copper is catalytic. You start with copper and you end with copper.
Right.
The problem with copper, with platinum, with palladium, with zinc as catalysts is that by and large, even though they can speed up a reaction, they can't speed it up very much.
Mm-hmm.
So even the catalyst that's in your catalytic converter that's getting rid of NOx from your nitric oxide from your exhaust of your car, it's not speeding the reaction up very much.
Mm-hmm.
So the fastest that these metals can speed up a reaction is probably 1,000 to 5,000 times.
Mm-hmm.
Whereas Ken knows, and I know because I've studied enzymes so long, there are enzymes that can speed up reactions 20 orders of magnitude faster, okay? That means that's a big number, right?
Yeah.
And the reason why the enzymes are able to carry out those reactions is because they're using their conformational flexibility, not just once, like in Bertozzi's work, but over and over again, because they go around and then they get set and do this again. Mm-hmm. And so why is this possible? Well, the metals are acting, I call them Procrustean catalysts. Mm-hmm. You know the story from Greek mythology of Procrustes. Procrustes wandered around Greece, and he carried with him a bed. And when he saw someone, he had them lie in his bed. If their legs didn't reach from one end to the other, he grabbed their legs and pulled them until their joints broke loose, because he was stretching them to that situation. When their legs sat out over the edge of the bed, he lopped them off, because what's happening with these metal catalysts is they're only taking things that fit into their little catalytic bed.
Mhm.
Whereas what enzymes do is enzymes use their conformational flexibility
Mhm.
to allow, not in a Procrustean way, but in an adaptive way, to catalyze the reaction.
They still have to be the right shape.
It has to
To
be
allow.
just the right shape, so the molecular orbitals, as we call them, are lined up so the chemistry that we want can occur.
Right.
Moreover, because, as I said, a protein is only made of L amino acids, then the protein is itself stereospecific. And so it's able, when it opens and makes a product, it only makes a product of one stereo form.
So now, just going a little beyond that, there are methods now, and AI is talked about and all that, to actually produce enzymes appropriate or configured, or can look at a chain of amino acids and tell you how it's going to fold.
Well, there are attempts to do that.
Yeah. Okay.
They've been partially successful, so that if you have a protein made up of, say, 100 or 120 amino acids, you can predict its structure.
Mm.
But most enzymes have 400 amino acids, and just this factor of 4 sounds like it's just a little bit, but the number of different microstates, all the different positions that they can take on, is bewilderingly great. And so even the fastest computers right now can't fold those structures.
Sort of
But
infinite.
people are getting there. And eventually, you see, we'd only know of a few enzymes that have only 100 amino acids. One that breaks down RNA has 128, Ken remembers. Any other questions?
Once again, an engineer thinks he understood what you said.
You're very welcome.
Any questions from?
I don't see any questions online. Ken Burns, any final question or comments?
Who is the chemist in Pavia?
Pardon?
I just wondered, since Silvana Riva was here last night,
Oh,
whether you knew of any chemists in Pavia that were
oh yeah.
involved historically in this kind of work.
Yeah. Ken's referring to a group at the University of Pavia that he likes very much, because what's so likable about his colleague is that he has invited Ken many times to Pavia. And I think he came here one time, I think.
He's here last night.
He was here last night? Oh, great. Not in your dreams. He was really here.
No, he's here. He's
Okay,
visiting.
good.
His son is on the faculty here.
I see. Oh, he's on the faculty. I didn't know. Yeah. Ah. Yeah.
Well, we thank you very much. We know we have next week, we have the Nobel Prize in Physics.
Yes.
Is that correct?
John X will be talking next week, and he shares some of the capabilities of Dan in terms of being able to at least partially make physics intelligible to a general audience. So we got John to agree to give the talk because last year's Nobel Prize stated that the people got the prize for solving complex issues in physics, so it's the first time I haven't seen the Nobel Committee actually give a clue as to what they were giving the prize for in the announcement. Anyway, John agreed to take on that task. John agreed to take on that task, so I'm looking very much forward to hearing him next week.